So, okay, I think I'm live now. Can all of you hear me? Hello. Let's
Yes, sir.
see.
Yes, sir.
All right. So, sorry, we are a little bit delayed because of people entering the session from different parts. So, I will be sharing the board with all of you. So, let's see. Um, yeah, so more people are joining in the main thing. So, let me share the screen in a specific window. Okay. Okay. Yeah. And let's see. All right. So one more thing is I will have to share this window from here as well. Okay. So, all right. So, can all of you see the screen in our internal class and as well as the
Yes,
external
sir.
people who are there? Okay, that's great.
Yes.
Thank you. So, we are here today to talk about the um, geometry and number theory part of the senior Olympiad. This is both for the Bose Mathematics Olympiad and the Australian Math Competition. So, as you perhaps know, that this particular event is hosted by Cheenta.com, and my name is Ashani Dasgupta. I'm one of the faculties at Cheenta. There is a set of supplemental materials available to this particular seminar in our Google Classroom, so you can use that Google Classroom for those additional stuff. If you don't know how to join it, I will help you at the end of this particular session. I'll give you the links to join it. Okay. All right. So now let me just start with a brief introduction about Bose Math Olympiad. It starts in August 2021. So I'll give you more specific dates are available in Cheenta.com. You can check out Cheenta.com for more specific dates. Its curriculum is basically number theory, geometry, algebra, and combinatorics. So it's the standard curriculum of different math Olympiads across the world. Some of you have also taken the research round in the Bose Math Olympiad. Some of you have already submitted. I think there are at least 20 people who have done that, 80 people who have done that all across the world. So that was a very big success because research is not something that everyone does. So whoever of you have done it, great. We are going to go ahead with that particular round. The Bose Math Olympiad is similar to the major math Olympiads across the world, like AMC, PRMO, SMO, UKMT, and so on. Perhaps you are also familiar with the Australian math competition. Many of you have registered for the Australian math competition. Um, with us. So we are registered with the Australian Math Association this year. We are officially approved to accept registrations. If you are an internal student of Cheenta, if you are an external student of Cheenta, really doesn't matter. Anyone can actually participate in it, and we can help you to do that. There is a curriculum for Australian math competition. It's very similar to AMC 10, 12. The senior level of the Australian math competition is very similar to that. So if you are in a math Olympiad program with us, if you are in a math Olympiad program or program or AMC program with some organization, maybe with Cheenta, maybe with some other organization, that would be extremely useful for Australian math competition as well. Okay, So today we will be interested in reviewing the major ideas from which will be useful for this particular contest. The both of them, the AMC, the Australian Math Competition, and the Bose Math Olympiad. Both of them, the senior level and the intermediate level, will be based on these ideas. So we will be discussing some of the ideas and maybe some illustration problems. Some of you have seen these ideas before and so on. Anyway, so you see, the first part that we will be covering today involves geometry. And one of the first things we talk in geometry is about the ratio of basis theorem. So I'll quickly draw pictures so that you can see what it is. Basically, the statement is extremely simple. The statement is like this, that if you have a triangle ABC, yes, this will be available in the Google Classroom actually. Yes. So I'll give you a link to that Google Classroom at the end of the class. So suppose we have two triangles, ABC and XBC. There are two triangles, ABC and XBC. Sorry. Okay. Hold on. This is very weird. Yeah. So just 1 second. Something went wrong. Okay. And here we go. Okay. So this is weird. Right. Okay, now I think everyone can see again. So I was talking about ratio of basis theorem, and it's quite simple actually. The statement of it is like this. So here is the definition, that if you have two parallel lines and if you have two triangles ABC and XBC, let's say the other one is here, XBC, like this, then one of the things about these two triangles is that if you drop a perpendicular from A or X to the other side, then the area of triangle ABC divided by the area of triangle XBC is equal to BC times this height 1 times half. This is the area of triangle ABC. This is the area of triangle ABC. And then divided by BC times height 2 times half. Height 2 is this one. But since they are parallel lines, height 1 and height 2 will be equal. So we have a very beautiful result that both of these are equal in area. So if these two triangles have vertices and bases between the same parallels, then the triangles will have equal area. However, if I draw another triangle, let's say YFM, like this, if I draw another triangle YFM, this particular triangle, notice that the height will also be the same, YFM's height. So I will write it here, ABC by YFM, the heights will be the same. Bases will be different, BC by FM times height will be the same times half will be the same. So basically you can cancel out the half, you can cancel out the H, and you can get the ratio of the basis theorem. That is, the ratio of the areas of the triangles is equal to the ratio of the bases. It's a very powerful but simple fact, and we use it all the time. Okay, so this is the thing. All right, this is happening over and over again. So I don't know why this is happening. It's hard for me to actually do it like this. Okay. So let's try this. All right, here we go. And I think you can see it here. Sorry for the disruption. This is happening over and over again, which is kind of irritating. Okay. The next thing that we want to talk about is the sine rule of area. It's a very familiar rule. If you have done trigonometry before, you know this. If you have a triangle ABC, then the area of the triangle ABC is equals to half times AB times AC times the sine of angle in between. So here is the angle that is in between AB and AC. So the entire area of the triangle is half of AB times AC times the sine of angle in between. There are many interesting consequences of this particular theorem. One interesting consequence, we will learn it in one of the next upcoming results, and that is the angle bisector theorem. So we will talk about it. But another result that would be extremely useful will be the area and similar triangles. This is one of the results that sometimes kids miss out, so I will talk about it in some detail. You see, if you have a triangle, let's say you have a triangle ABC, and you have another triangle XYZ. You have two different triangles, ABC and XYZ. What can you say about the ratio of the areas of these two triangles, ABC and XYZ? What can you say about the ratio of areas if the two triangles are similar? Now, sometimes there is a little bit of confusion about what it means to be similar triangles. So there are two definitions of similar triangles actually. There are two ways you can think about it. So I'll write it here. The definition one, they are equiangular. And definition two is sides are proportional. And one can show that these two definitions are actually equivalent, whether you have um, when you have whether you have equiangular triangles or whether you have proportional sides triangles. They are this, that actually leads to the same concept. For example, we can draw pink angles here, we can draw red angles here, and we can draw blue angles here. Okay, so the three angles of these three triangles are equal to the three angles of the other three triangles. That is one way to think about it. The other way to think about it is that the corresponding sides are proportional. Now, sometimes kids have problem in understanding what is the meaning of the word corresponding. What is the meaning of the word corresponding sides? So I will write this down. Corresponding sides. I always confuse myself how many R's and how many S's are there in the word corresponding. So you can please pardon me if I have got the spelling wrong. But what does this actually mean? Corresponding sides are proportional. So what does this particular phrase mean? Well, it is very simple. What you do is you look at the sides which are opposite to equal angles. You look at the sides which are opposite to equal angles and you say, okay, those are corresponding sides. So in our context, you can easily check this, that BC and YZ are corresponding because they are both opposite to the pink angle. If you already know this, it's very easy for you. But if you do not know this, think about it. If you are seeing this for the first time, this is a major area that kids make a little bit of mistake. So I just want to point this out, stress this fact. Okay, Uh, the side opposite to the red angle are also called corresponding sides. So AC, let me write it in red actually. AC and XZ are corresponding. And similarly, can anyone else tell me which are corresponding sides? Which are the other two corresponding sides? Can anyone tell me which other pair of sides are corresponding? Okay, let's hear it from Parth. Parth, tell me, what do you think?
and YZ and AC and also AB and Bisector.
Okay, AB and okay, opposite to the blue side, we have AB and XY, correct? AB and XY. So one way to talk about, so the pink sides are corresponding, the red sides are corresponding, and the blue sides are corresponding. See, color coding is a very important strategy which I often use to explain something to myself. It becomes very easy when you color code. You have an additional dimension in your mind to explain stuff to yourself. So it's kind of useful learning technique. So what the second definition tells us is that all of these ratios are equal. And what the first definition tells us is that the angles are equal to each other. Okay. Okay, that's great. Now, I was interested in the notion of area and similar triangles. So what can we say about the ratio of areas? So here is a very important result that people often use in problem solving. That is, this is equal to the square on the corresponding sides. Ratio of areas of similar triangles is equal to squares on the corresponding sides. So this is a very useful tool, and how to prove this, we don't have time to show that here. It's a very beautiful proof, but I don't have really time to show that here. You can try to prove that in your home. Okay. All right. The next thing that we want to talk about um, is the Carpet theorem. So this is a very so I'll just go ahead and clear all. Okay, so here is a very important sort of idea. Maybe you have seen this before. Let's see. So this is known as the Carpet theorem. So there is an excellent book by T2 Andreescu. Uh, Maybe some of you have read that book. I will give the link of the book or name of the book in Google Classroom actually. It's a fantastic piece of mathematical tool, and here is what it says. I mean, you can quickly use it to do certain problems. Suppose you have a square ABCD. Suppose you have a square ABCD, and you take any point here, let's call it X, and join AXD. And you take another point Y here, doesn't matter which point, you take that point, you draw this. Okay. All right. So you draw this. All right. So we learn Carpet theorem with a lot of examples and problems in our main math Olympiad program. But here it here is one such problem, and you can check it out. I will mark the red region. I will mark the red region, and I will also mark the green region. Okay, I will also mark the green region. And what we want to show is that the area of the red is equal to the area of the green. That's our contention. Okay, that's what we want to show. So how do we show this? That's the question. So before I answer the question, before I go ahead at the solution, I saw a raised hand. Couple of questions are there. Tejas Kulkarni is asking that where can we register for the Australian math competition. I told in the beginning of this discussion that Cheenta is now registered, is a registered school with Australian Mathematical Association. So you can register with Cheenta for the Australian math competition. You do not need to be an internal student of Cheenta. Cheenta is just a school that, or an organization that is officially approved to register students, so we can help you to do that. If you want to do it, you can just email us. Of course, if you are an internal student of Cheenta, if you take a math Olympiad program or something with Cheenta, then you are already in connection with our admins and they can help you. Okay, so we have raised hands inside the Google Meet. Parth, Vartak, and Aryan Prakash. Okay, Aryan, let me hear it from you. What do you have in mind?
Check my hand because I had a proof for this
Oh, you have a
theorem.
proof for this? Okay, go ahead. How do you think we can show this?
So first, we show that the area of the triangles AXD and DYC are the same. That's because the base and the height for both of them are equal because it's a square.
AXD and DYC, these two
Have
triangles have equal area because they are both half of the square, right? So you can check that out, that both of them are half of the square. Okay,
So then
so
the height part, the quadrilateral which you have left out in both the triangles, we subtract that area from both the triangles, and we're left with the green on one side and the red on one side.
correct. If you subtract the white, from AXD and subtract the white from DYC, you are left out with the green here and with the red here. So that's how you show that these two are equal. You don't even have to compute the areas of the red and the green. This is a standard strategy. It's a very beautiful strategy actually. So this is usually known as carpet theorem. So when you are facing problems like this, look out for this kind of strategies. Okay. More strategies like this will be available in the Google Classroom that we have, so you can check that out. Okay. The next idea that we have is of the incenter and area. So we are dealing with area problems. Okay, Nijhar has also given an idea. Okay, that's great. All right, Nijhar. So let's go ahead with an incenter and area. This is a very important tool. So let me talk about that. So suppose we have a triangle ABC like this. ABC is a triangle. And we have a point inside the triangle called the incenter. So if you don't know what the incenter is, it is the meeting point of the angle bisectors. So incenter definition is the meeting point of angle bisectors. So if you draw the bisector of the three angles A, B, and C, the three angles A, B, and C, if you draw the angle bisectors, one can show that they all pass through a single point, and that particular point is the incenter, which is the point I. Okay, now it is possible to draw perpendiculars from the point I like this, and you can show that Ix, Iy, and Iz are all equal in length. They are all equal in length. And this particular length is known as the in radius of the triangle. So a lot of geometry is going into this simple set of statements, because I have to prove each of these statements, otherwise I cannot claim it. I cannot prove them in this particular lecture, because of course it's just an overview. In a main geometry program for Math Olympiad, you will be able to see proofs of all of these sentences, but you can also try to prove this on your own. Okay, so now you can draw a circle with I as the center and Ix as the radius. This is known as the incircle. Now there is a very beautiful relationship of the in radius, this is the sense small r, with the area of the triangle. So I will help you to color code and understand what this relationship is. If you look at this particular triangle, this is IBC, this blue triangle IBC. If you want to find out the area of IBC, this will be half BC, the base, times the small r. This small r is Ix, because this is a perpendicular, right? I just said that Ix is the in radius r. So I can just write half BC times r. Similarly, this is the blue triangle IBC. Now let's draw the pink triangle IB, IAB. The pink triangle IAB is half times AB times R. And we have the red triangle IAC. Here we go. The red triangle IAC is half times AC times R. So we are using a couple of facts here that Ix, Iz, and Iy are all small r. They are all the same. So one has to prove such a claim. We cannot just arbitrarily say this. So try to prove that. And then obviously they are perpendicular. That's how they are drawn. So we can use them as heights of the small triangles. Okay, we are almost done. So what we can do is we can add all of these up. So IBC, IAB, and IAC, we can add all of them to get the triangle ABC. You get the entire triangle ABC, the area of the entire triangle ABC, which we will denote by delta. This will be half times, you can take R common, because R is in all three of them. You can take R common, and then you can add BC, AB, and AC. So BC plus AB plus AC. Okay. So now there is a way to write this thing as in a condensed form. You can write it as half times R. Okay, half you can take in. Half times BC plus AB plus AC is sometimes known as the semi-perimeter, because BC plus AB plus AC is the perimeters. You take half of that, so semi-perimeter. So R times semi-perimeter S. It's a very beautiful formula. Delta equals to R times S, where delta is the area of the triangle, R is the in radius, and S is the semi-perimeter. Semi-perimeter means you add all the sides of the triangle and you take half of it. So delta equal to R into S is a very non-standard type of equation or formula that gives you area of a triangle, and it is often used to solve problems like this. Okay. One last thing that you should look up is the area of quadrilaterals. So that's the one last thing, in the sense that you should have the areas of quadrilaterals in your mind. So for example, if you have a trapezium, or if you have a rhombus, or if you have a parallelogram, how can you compute the areas of each of these quadrilaterals? And I would not go too much into this because this is very standard literature. You can always try to learn this from somewhere. But this is something that you should definitely know before going into the Olympiad. Okay. All right. So let's go ahead and go to the next one, next part. We want to talk about triangle geometry. I've already discussed what is similar triangle. Of course, many of you know midpoint theorem. It's extremely beautiful and important. You take a triangle ABC. If you take the two midpoints M and N of the triangle, and if you join them, then Mn is half of BC and Mn is parallel to BC. That's the standard result for midpoint theorem. We don't want to actually spend time proving anything today because we are just giving an overview. Okay, so the next thing will let us revise something quickly. So the next thing is the angle bisector theorem. It's a very important result, but it will also help us to revise an idea. So let's go ahead and talk about the angle bisector theorem. So I'll just talk about the internal angle bisector. There is an external angle bisector theorem as well that you can use. So what is it? So if you take an angle bisector, let's say AD, suppose AD is an angle bisector, then I want to compare the areas of triangle ABD and the area of triangle ACD. And I know by ratio of Basis theorem that ratio of these two triangles, areas of these two triangles, is equal to BD by CD, because ratio of the areas of these two triangles, ratios of the areas of these two triangles is equal to the ratio of the bases. They have the same base and the same vertex. So that part is simple. But now let's compute the area of triangle ABD and area of triangle ACD. So what is the area of triangle ABD? In the previous discussion, I told you about the sine rule. So we will be using the sine rule actually. It's half times AB times AD times sine of this angle. Let's call this angle theta. And the area of triangle ACD is equals to half times AC times AD times sine of angle theta. Okay, so if you take the ratio of them, that's what we want, ABD and ACD, we want to take the ratio of them. So we cancel out the half, we cancel out AD and AD, we cancel out sine theta and sine theta. So we are left out with AB over AC. That is the result that we are after actually. So this is equal to AB over AC. It's a good revision of what we just talked about, that sine rule of the area of triangle or ratio of basis theorem that we talked about. So all of them come into place. We have AB over AC equals to BD over CD. It's a very standard and useful tool to solve geometry problems. Okay, so now let's go on to centroid. That's the next idea. It's a very powerful tool. Centroids are often used to design problems actually. Now, one of the things that you need to know, first let me define what a stress centroid is. So ABC is a triangle. If I'm rushing, I'm sorry really. I don't want to rush, but there is so much stuff to cover in one session. But you can always see other videos in cheenta.com. There is a lot of resources here. You can, and other places, of course, there are many other resources online. I'm just trying to compress the stuff that you will need in the next upcoming Olympiad. That's it. It is not exhaustive, but it will at least give you a starting point. Okay, so what you do is you draw the medians of the triangle AD. So one of the things that kids miss out, so here is a caution point. So here is a caution point, something that you should remember. And this is how I think about it. Median splits the triangle into two equal area parts. This is almost obvious, but when we see a median, it's sometimes not the first thing that we think about. Of course, we think about a bunch of stuff. We understand that median splits the triangle's other side into two equal parts and so on and so forth. But it also does something to the area. It's a very simple thing. We can easily use ratio of basis theorem to prove this, but we often it's in our mind space. That's what I'm trying to say when we think about median. So remember this. Remember this. It's often very useful while solving problems. Okay. All right. So what does medians have to do with centroid? Well, everything. You can create the three medians, the red, blue, and the pink one. And it's a theorem that all of these three lines pass through the same point, and we call that point G. This point is G. So this point G has many beautiful properties. One of the properties is that it is a splitting point which divides the medians into 2:1 ratio. So AG by GD is 2:1. That is one of the ways you can think about this particular point G. It is a point which splits the median into 2:1 ratio. Here is an exercise that you can try. It's a very easy exercise. You can use the median. You can use the ratio of basis theorem to show that G in fact does what I'm saying it does. G splits the medians into 2:1 ratio. It's a very important tool in geometry. I will not speak more about the medians, but beware of medians. They create a lot of problems. Uh, a lot of problems are created using medians actually. Let's go to circumcenter and the sine rule. It's the next idea. Okay, sorry. Right, I don't know what's going on. Okay, okay, here we go. Okay. Okay, so yeah, here, sorry. Circumcenter and the sine rule. So it's a very interesting and useful tool of geometry. So I'll just draw a triangle ABC, and I will draw the circumcenter of this triangle like this. So it's a triangle. It's a circle that passes through all the three vertices of the triangle. And suppose O is the center of this circle. So O is known as the circumcenter of the triangle ABC. And there is a very useful theorem which says that sine of angle A by small a is the side opposite to angle A. So I'll probably color code it again. This is red, this is red, this is pink, this is pink, this is green, and this is green. So the small letter is reserved to mark the side opposite to the angle. So for example, this one is small c and this one is small b. So sine A by A is equal to sine B by B equals to sine C by C is equal to, one can probably prove prove something related to the entire triangle, that you can write this in a in this way. So this is twice the radius or the diameter. Maybe you can probably say it's a diameter if you flip this over. Okay, if you flip this over. So now you can also relate, this is an exercise, you can relate this to the area of the triangle. That's a useful exercise that kids all do all the time. So you should try to do this using area formulas of triangle. Okay. Now let's move on to the next thing, which is the cosine rule. I must say that there is a very beautiful problem using cosine rule that one of our faculty members, Shampod Kaur, posted in YouTube, our YouTube channel. It is from CMI entrance. He used the cosine rule and geometry to solve a problem from algebra. So you can try to check it out in Cheenta's website. Okay. So Cheenta's YouTube channel. I'm sorry. So okay, what is the cosine rule? It has a very important function actually. Suppose we have a triangle ABC, and we know theta, this angle theta. We know the side length AB, and we know the side length AC. So you see, philosophically speaking, we should be able to tell what is BC, because AB and AC tells you how much the triangle, AB and AC gives you the two sides of the triangle, and the theta tells you how much it opens up. So theoretically speaking, you should be able to tell what is the length of BC. Now, how do we do that? Okay, that's how the cosine rule is created. So BC square is equal to AB square plus AC square. Well, this is true if it is right angled, but if it is not right angled or otherwise, I mean, even if it is right angled, this will be actually true. So minus 2AB times AC times cosine of the angle in between. So this is the extra term that you have to worry about if it's not a right angle triangle. So maybe I can write it a little bit clearly here. AB square plus AC square minus twice AB times AC times the cosine of the angle in between. That gives you the length of BC square, the value of BC square. So this is a general tool that we use all the time, And one of our, as I told you, you can see its application in a problem in our YouTube channel. It's a very beautiful application actually from CMI entrance. Okay, let's move over to the geometry of circles. There's a bunch of things that we do using in circles. One of the things, maybe some of you know already this, that if you have an angle point O, take the 2 points A and B. This angle is known as the angle at the center, And if you take any other point on the circumference, let's say P, then APB is known as the angle at the circumference. But the good news is both of them are subtended by this red arc. So what is the meaning of the word subtended? Sometimes kids have problem with this word. They do not understand. I also did not understand this word when I was a little kid. So subtended basically means that the feet of the angle is at the end points of that arc. That's all that it means. So when I say this APB is subtended by AB, what I mean, the feet of the angle APB is on the end points of this arc AB. And when I say AOB is subtended by AB, I actually say the same thing, that AOB, the feet of that angle, feet means there are two sides which are sort of going up to infinity. So you take any 2 points there. So feet of the angle of the two legs of the angle are there. Okay, so this is theta by 2. That's the theorem that angle at the center is twice the angle at the circumference. Okay, so this is a useful tool. We have already talked about cosine rule. That's great. We have one big theorem that is coming up, which is the tangent chord theorem, which we often use to solve problems. So it's a very important problem. You should definitely know this. See, if you have a circle and the center of the circle is O, suppose you have an external point and you draw a tangent from that external point to the circle. Suppose this point of tangency is A, this point is P. Okay. Tangent means this is touching the circle at exactly 1 point. And in fact, it's a very important fact or theorem that OA, the radius, is perpendicular to the tangent. So the radius is perpendicular to tangent. It's important to know that in many problems. Okay, so now from the point A, let's draw a chord like this, AB. Let's draw a chord. Now suppose AB, this arc AB, is subtending an angle theta here. Then it will also have an angle theta here. So the angle that the tangent makes with the chord, is same as the angle the chord makes at the other end of the other side of the circle. So this is sometimes known as the alternate segment theorem. Alternate segment theorem. It's a very important piece of tool in geometry. So if you think about it again, the key components of this theorem is that you have a tangent like this, you have a chord like this. The angle that the tangent makes with the chord, this theta, is same as the angle that the chord makes on the other end of the circle. That's how you should think about it. Okay. So this is great. This you can try to prove this theorem using angle chasing and the stuff that we have already discussed in the previous slide. So you can use that. But that brings us to one more powerful theorem, that is the power of a point. I cannot even say how much important is this power of a point thing. So in fact, if you have seen if you are in some of the geometry lectures at Cheenta, Math Olympiad program, or if you have seen some videos in Cheenta's YouTube channel, you will know that this is very deeply related with inversive geometry. There is an excellent book by Coxter that you can probably look at uh, and learn how power of a point is related to inversive geometry. But here is roughly what it means. If you have a circle P, you want to know how far is P from this circle. You want to have a measure of how far is P from the given circle. And here is a strategy that you can always use. You can draw a secant. If the point is, of course, outside the circle, you can do it. You can draw a secant and you can simply multiply PA times PB. Turns out it doesn't matter which secant you draw. In fact, if you draw a different secant, let's call it x and y, where it hits the circle, then if you count px times py, if you compute it, it will be same as pa times pb. It doesn't matter which secant you draw. In fact, if you draw another secant, let's call it r and s, where it hits the circle, and if you multiply pr and ps, well, that will be the same thing. So this property, this is an invariant property. Invariants have a very powerful role in Olympiad geometry. Invariant property of the point P, and we call it the power of P with respect to this circle. So of course this is equal to some constant K. If all of these products are same, means it's equal to some value, some number. For a given point P, that number is constant. In fact, if you draw a tangent from P, let's say PQ, you can think about this tangent as a secant that hits both of the lengths are equal, in fact. So it is equal to PQ times PQ, or PQ square. So if you draw a tangent, it will be equal to PQ square, the length of the square of the length of the tangent. If you draw a secant, then it will be like the two different lengths, you can always multiply them. So this is a constant, and this is often very useful to solve problems, and you should definitely have a look at it. You can try to
how
prove.
it is PQ square?
Sorry?
Can you explain? Sir, how is it equal to PQ square?
Okay, that's a good question. Let's try to prove this. How is it equal to PQ square? So though we don't have time for proof, but I can give it a try in the little bit time that we have. If you look at triangle PQR, and if you look at triangle PQS, you can show that these two triangles are similar. These two triangles are similar. Why is that? Well, I just talked about the chord tangent chord theorem. So the blue angles are equal. You can easily see that. Angle P is common in both of the triangles. If you look at the triangle PQR and PQS, the blue angles are equal because of the tangent chord theorem that I just talked about, and the pink angle is common in both of them. So the remaining angle will automatically be equal. So the remaining angle, let me mark it in red. In the big triangle, it's this red angle, and in the small triangle, it is this one. Okay, so now we know that these two triangles are similar, so we know the corresponding sides are proportional. So let's look at the sides opposite to the red angle. Red angle's opposite side is PQ, red angle's opposite side is PS. So PQ over PS is equal to, let's look at the blue angle. So blue angle's opposite side is PQ again, and here the blue angle's opposite side is PR. So we can write it as PR by PQ. Now if we cross multiply it, we get the desired result. PQ square equal to PR times PS. So this is the standard proof of power of a point theorem. Okay. Now the next thing that we would like to do is to go into number theory. Unfortunately, we are out of time today, so we will not do that. We will not rush through this entire process. We will go another day for number theory. For today, you can check the link in the description for the YouTube video, or you can ask me separately at helpdesk@chinta.com for link to the Google Classroom. Okay, you can email there. So I hope all of you have learned something today. If you have questions, feel free to comment in the YouTube video, and I'll be able to respond to that in time. Keep on doing great
How
mathematics,
do we
everyone.
join the classroom? How
Yeah,
do we join the classroom?
yeah, we will. I can give you the link for that. I will do that in a minute. Okay.
Okay.
Okay. Thank you, everyone. Bye.